Hello, welcome back. So I'm going to introduce the method of joints here. I'm going to go through the technique, we're going to take a break, then I'm going to come back with a problem. Okay, so the method of joints. So what you're going to do when you analyze a truss this way is you're going to satisfy the conditions of equilibrium at each joint. So therefore the equilibrium of forces. Okay, so your steps are, first, make a free body diagram of the entire structure. This will give the reaction forces at the supports. Use usual tools, sum of the forces equals 0, sum of the moments equals 0. All right, then you're going to free body diagram each joint. This means find the forces acting on each joint. The forces in the members. That connect to the joint. Okay, so if we had, let's say we have this guy like this, and like this, and a horizontal member here. We're going to call where they come together A. I'm going to call this connection up here B, this connection here C. And there's some weight hanging from this. Okay, so this is our diagram of our structure. The FBD of A looks like this. You've got the weight hanging down, and you've got force here, you've got a force here. And I'm not taking account directions. I'm just drawing in. It's obvious that these can't both be this way, right? And be in equilibrium. They can't both be pointing to the right. One has to be pointing to the left, or else this thing's going to be accelerating to the right. Right? This angle has to be the same as this angle. Okay, since they're two force members with only two forces acting on it, the forces must be equal and opposite. Okay, so the forces always act along lines of the member connecting at the joints. Because these are two force members, so the forces are always going to lie along. They're always going to lie along the line of the member. All right, so we're going to redraw this guy. So let's put A here, B and C here, and now that's more realistic, but until we analyze, we still aren't sure if we have those in the right directions, you would think, but we do know this is the right direction. Can you figure out why? That's right. Okay, if you look at B and W, those are the only two with forces in the y direction, right? B and W are the only forces with components in the y direction. Therefore, the component of B must be opposite W. Or it's going to accelerate toward the ground, which we call collapse. Okay, so that means that B has to be pointing upward like this, and if it's pointing upward to counter the W, that means its x component has to be pointing to the right, right? So it's going to have an upward component to balance the downward W. That means its x component has to be balanced by C going to the left. So that's the kind of thought and analysis that's going to have to go into this. And that whole two force member thing helps us a huge amount here. Right, so once we know the forces on a joint, we know the forces on the member that connect it to the joint. Right, so that member AB, okay, this is A, B. Let me move this a little bit. A and B. So, if there's the point, we're kind of doing an exploded view here. A and C. All right, so we know that at point A, the forces are like this, and like this, right? So in the member, they must be opposite. Right, so that means this guy has got to be in tension. And this guy has got to be in compression. Right. In real life, loads can shift, so members may switch from tension to compression, unless, of course, it's a chain or a rope or something like that. All right. So that's our basic method for doing a method of joints. I'm going to stop there, and I'm going to come back with a problem. All right. See you in a minute.